Where we ended last week was looking at molecular orbital theory, and I said we were going to look at what happens when we overlap p orbitals. Right? I've changed my mind. We're not going to look at p orbitals, and the reason we're not going to look at p orbitals is because it really only applies to strict molecular orbital theory. And we don't use strict molecular orbital theory. We use kind of a blended approach. We take the information that we learned from hybridization and the information that we understand about how orbitals overlap and what they interact to produce from molecular orbital theory. Right? So the first thing I want to address here, because a couple people have asked questions about it, is that if we compare the s orbital to the p orbital, so let's ignore most of the content that's on there. There's an s orbital, and then we have our p orbital up there, right? What do you notice as differences between the s and the p? What do you mean 1 versus 2?
Visually.
Visually, okay? The s orbital is just a single sphere. The p orbital has 2 lobes. Okay? What else? Okay. There's a spot running through a p orbital, okay, where the electrons do not exist. Okay. That spot is known as a node. Okay. So where our electrons cannot exist. So any place we see kind of a shrinking of the probability like that, it's shrinking down to an infinitely small probability, and we have a node. Okay. What happens around that node, actually before we even do that, if we take a look at the s orbital, where's the node in the s orbital? There isn't one. Okay? There isn't a planar node. Okay? So what else comes out of this comparison then? If I were to color the s orbital, I would probably color it something like this. It is always a single phase, and this always trips students up because we reference the phase as positive and negative. When we're talking about a wave kind of has that nice up and down action. If I froze and looked at my hand now, my hand is above the x-axis, so I would refer to that as being a positive aspect or a positive phase. If I continue the motion, at some point, I go below the axis, in which case I have a negative phase. That's what the positive and negative are referencing. It's the phase state because electrons move like a wave. Okay? Across a node, the phase changes. Because there is no node in an s orbital, there is no phase transition for an individual s orbital. It is either all positive phase or all negative phase. If we move to the p orbital because of that node, one phase will be positive, one phase will be negative. Always. Okay? This can be shown by having them in separate colors, red versus black, shaded versus not shaded. All we're trying to address is the phase aspect of this. It is that phase aspect that allowed us to form bonding interactions and anti-bonding interactions when we overlapped 2 s orbitals. Okay? So how do we then use this to our advantage later on? Well, if we move to kind of our hybrid version of this, what we're going to start to use is now not just the atomic orbitals, but we'll use hybrid orbitals. Okay? That sp orbital is really spx. What is that x in reference to?
Direction.
Okay, we could go with a directionality off of a coordinate plane. Not a bad idea, but no.
Not positive or negative.
In fact, it might make it better if I put it in the other spot. It's the number of p orbitals being used. When we're talking about the sp orbitals in this sense, the sp hybrid orbital looks the same as the sp2, looks the same as the sp3. Okay? There is no easy way to differentiate those when we go through and draw them so they look the same. Right? So let's just pick an S, and a P. All right, let's go through and shade. The S is red. The P has its two nodes, red and blue. What happens if those two orbitals now interact with each other or overlap?
The red would overlap each other.
The red overlaps. They're in the same phase, which means an electron in the S orbital can jump to the P orbital, okay, as long as it's in that position. So if I looked at my nucleus, the electrons can exist out here. What happens in the blue section? Right. Now they're out of phase. They cannot interact. The result being we end up with unsymmetrical looking p orbital. Okay. All our sp3 orbitals look like this. Okay. They will all have a node moving through the middle of them. Okay, so we have a change in phase across that. Okay, so let's look at the bonding between two carbons. Okay, and in this case, I'm going to look at a double bond. Okay, when we go through to look at this, we have to evaluate what orbitals were used to make each of those bonds. Okay, it can help if we tag on the extra hydrogens. What hybridization do we have for each carbon? Let's make it Christmassy, as you know, Christmas in February. So sp2 I heard. So let's go through and look at an sp2 orbital for each of those. So those are our atomic sp2 orbitals coming in to interact. That would make one of those bonds. Okay. When they come in to interact, there's the possibility where they are in the same phase. The result is that the electrons can now hop between one atom or one nucleus to the next, and we would get an image looking something like this. Everybody see that? Because when they get near enough to each other, there's a small section where those orbitals overlap. That orbital overlap, because they are in phase, means I increase the probability of finding electrons, and I end up with that drawing. Okay. This should naturally be lower in energy than the bond or than the atoms on their own. Why would that be the case? We'll flip it. What would it mean if our bonding orbital was higher in energy than our atoms? To form a bond, what must all things do? They would have to go up in energy. What is our natural state of everything we've seen? It goes to lowest energy. If our bonding orbitals were higher than our atomic orbitals, do we ever see a bond? No. So naturally, it makes sense for our bonding orbital to actually be lower in energy. Conversely, we could go through, if we put an electron there, we've given the electron more opportunity to move. It can jump between both systems. More space, kind of like resonance, means more stable. What happens if they aligned and they were now not in phase? Well, the atoms are still in the same location, but now the electrons aren't allowed to be in that space. So the result is that we see our electrons push outwards. If we go back to our conclusions, or what we talked about with our nodes, what happened? I started with 2 nodes, and the next highest molecular orbital has 3 nodes. Every time I go up in energy, I increase the number of nodes. Okay? I want to be able to name these new molecular orbitals. I could just name them 1 and 2, Bob and Sally, but we pick names that have some origin back to where they came from. Right? This was involving a direct overlap of orbitals. So we've gone through and defined the direct overlap of orbitals to be a sigma bond. So instead of calling these 1 and 2, I could go through and call them sigma 1 and sigma 2. Instead of just listing out the numbers, I've now applied information about how those orbitals interacted. I've said that there's a direct overlap to them. That's why I have the sigma specification. Is that bond the same, or that orbital the same? Clearly not. One's 1, one's 2. Is there something more that's different about them? And the bottom one, where do our electrons spend most of their time? Between the atoms. And the top one, where do the electrons spend most of their time? Not between the atoms. Okay? So I could add some information and refer to the bottom one as a sigma bonding orbital. Okay? The word bonding does not mean necessarily that there is a bond. It just means that is a favorable interaction. Okay? That orbital exists. Well, on the top one, it's not a bonding orbital because I don't have electrons between the atoms. Okay? So I could call it, well, not bonding. The problem with calling it not bonding is what were our atomic orbitals? They were also not bonding. Are the not bonding orbitals of our atomic orbitals the same as the not bonding of our molecular orbital? No, that's why we could hear the word atomic versus molecular. So we invent a new term for that orbital. It's just a name, just like bonding. But I can't use not bonding. Instead, I'll use anti-bonding. Specifying that as sigma 2 anti-bonding is a lot. So I want to change my notation to accent the fact that I have anti-bonding, and that's where I can change that to become sigma star. Okay? I've now described the direct overlap of those orbitals to make that sigma bond in 15 minutes. Okay? Questions that could get asked. How many nodes are in the sigma bond for ethylene? C2H4. A deceptively short question with multiple choice answers 0, 1, 2, 3, 4. Well, that seems really easy. It's got to be 1. No, that was wrong. It's got to be 2. Well, that's wrong. To answer that question, that short little silly question, that has to get drawn. You have to either draw that in your head or draw it on paper. There isn't just a, well, it's this answer. Okay? You have to understand where it's coming from. That's why you have to draw it. Once it's drawn, the question becomes easy. How many nodes are in the sigma anti-bonding orbital for the carbon-carbon sigma bond in C2H4? Well, there's one section where I can't have electrons. There's a second. There's a third. There's now 3 nodes. The answer becomes obvious if you draw it. If you don't draw it, the answer is virtually impossible, and you're just shooting in the dark. Okay? We talked about things that are important to keep versus not important to keep. I decided nomenclature was one of those things that's not important to keep, so I ignored it entirely. Okay? I accepted the grade that came out of that. Okay? Molecular orbital theory is an important concept, but it is not required, per se, to do well in OChem. If you want to decide that this content is not something that you need, you can accept the point loss, bless you, on those questions. If you decide it is important, then you should figure out how to draw these. Okay? As far as that level of importance, at ASU there's an instructor that feels molecular orbital theory is so important, he devotes virtually the entire semester to molecular orbital theory. Okay? His students can do better for it because they understand the theory of how bonds work. Okay? That's the students that go through and work through molecular orbitals and spend the time to understand it. The students that don't usually fail the class. There's no in-between. Right? I'd like to provide a little bit of a cushion or an in-between. That's why we don't devote the entire semester to it. Right? If we now look at this, I can now dump 2 electrons into this. Okay? So at this stage, there's no electrons in my drawing. How many electrons came from the carbon with the sp2 orbital, the left carbon? Well, carbon comes in with how many valence? 4 valence. We dump 1 into each of the sp2 and 1 into the leftover p orbital, which means each carbon brings in a single electron. Where do those single electrons go in the molecular orbital bond? Where's the first one go? Where's the first electron for hydrogen go? Where's the electron for hydrogen located? The 1s orbital. Why not the 2s orbital? The 3s, 4s, 5s? Hydrogen absolutely has those orbitals. Why aren't they filled? Where do we put our first electron? The lowest energy. Where's our lowest energy molecular orbital? Sigma 1. There's our first electron. Where's the second go? The lowest energy. There's our second electron. Right? Go back up to our drawing. How many electrons are between our red and green carbons? 4. Well, that means we have to put 4 in. If we put 4 in, 2 more electrons come in. Where would those 2 electrons go? Where's the lowest energy? Where's our lowest energy molecular orbital? We have this one, right? How many electrons can we put into it? 2. How many electrons are there? 2. So you can't put any more there, right? Where do you put the next 2? In the next available molecular orbital. If we did that and then averaged the energy of our electrons, we would notice that the energy of our electrons is higher than that of the atomic orbitals. What would that mean? That means you have no bond. The structure says, nope, you've put me at too high of an energy state. I'm not going to exist anymore. The bond doesn't happen. But the bond does happen. So those 2 extra electrons have to go somewhere. But they can't go into our sigma drawing. I wonder if there was another orbital left over on each of these that we could have placed those electrons.
I'm guessing.
Yes.
What was our hybridization for the red carbon? sp2, which means how many orbitals did we use? We used an s and we used 2p. There's a leftover p orbital. What is that leftover p orbital doing? Okay, well, here's where we have to clear everything. Sorry. And we look at that leftover atomic orbital for our p orbital with a positive, positive, negative. Let's not specify that phase. What are the possible ways that these 2 can interact? Well, they could be positive, positive, negative, negative. What does that mean? They're in phase, which means
They can interact.
they can interact. An electron can jump back and forth. Okay. We've increased the probability of finding the electrons between the atoms. The way that we typically draw this would be something like this. What if they came in and they were out of phase? Can they interact now? What does that mean? Those orbitals literally bend away from each other. I don't want to see you, go away. Okay. Leaving a magical node in between. How many nodes do we have in the first one? How many nodes do we have in the first one down at the bottom? 1. How many nodes do we have in the second one? 2. We've increased the nodes. Is this the same type of interaction that we saw with the SP hybrid orbital? Okay. Should be vigorously shaking your head. No, because the orbitals don't overlap. How come the electron's allowed to do the jump if it's not overlapping? That's quantum tunneling. Yay, quantum tunneling. Okay. That quantum tunneling allows for the electrons to jump back and forth between the orbitals. Okay. So we have a type of bond where there's no quantum tunneling because they directly overlap, and we have a type of bond where there is quantum tunneling where they don't overlap. I want to be able to differentiate this bond from the other one. So I need a new name. Can't call it sigma anymore. This is where I go back to the origins of what made this overlap. What orbitals did I use? I did not use S and P. What did I use to make this overlap? P and only P. So it's a pi interaction. The bottom one would be pi bonding. Why pi bonding? Because the electrons could tunnel back and forth. The top one becomes pi anti-bonding because they can't jump back and forth because of that node, because they're out of phase. Okay? We now have an explanation. That extra electron that was in there jumps into this lower energy molecular orbital. It does not exist in the exact same space as our sigma. Note, where are the electrons here? Above and below the plane where the sigma bond was formed. I can't put more electrons into the same orbital. It has to go into a new one. Has to. That's where we get the pi bond. Okay? Exciting. Yay. Okay? So if we scaled this up, which the textbook does, and they're looking at a full molecular orbital diagram, what we've shown here is all the atomic, or the sort of atomic orbitals for ethylene, C2H4. Our hydrogen shown in red, the carbons are little white dots in the middle. Okay. Each of those carbons becomes sp2 hybridized because they have 3 groups of electrons. So the hybrid orbitals are shown in purple. And then the unhybridized blue orbital is the last remaining atomic orbital. I could then go through and describe the molecular orbital diagram. Okay. Well, what type of interaction is happening? That's not a very good pointer. Where that little arrow is, what kind of interaction is happening there? That's an overlap. Direct or indirect? Direct. What type of bond is that? Sigma. So that single space generates a sigma bond because they are directly overlapping. But that's assuming they're in phase. What else is generated? A sigma star. How about the next position in front? I have yet another sigma interaction with a bonding and an anti-bonding. So I would now be up to 2. But I've got hydrogens in the back, right? Each of those are going to generate a sigma interaction. So we have 4 sigma bonding and we have 4 sigma anti-bonding. Okay, we haven't addressed what's happening with the carbon. So in that little red box, what's overlapping? There is no hydrogen in that little red box in the middle. Carbons. It's 2 carbons. What orbitals are interacting in that red box? sp2 orbitals. What type of overlap is that? Sigma, which means, whoa, it's not 4 anymore, it's 5 sigma interactions. But if I have a sigma bond, I also have sigma antibond. Okay. What's remaining? We also have the pi bond. Where would I expect that pi bond to be? Higher or lower than in energy than the sigma?
Higher.
Why should it be higher than the sigma? Because you didn't draw any space below that. Yeah, fair answer. Try again. The sp orbitals are lower in energy than our p. Is that true? Yes, that's why we fill the s before the p. Yeah, that was true. Which means our pi interaction is a little bit higher up. How many pi do we have? How many p orbitals do we have? 2. How many pi orbitals do we have? 1. How many pi star or antibonding do we have? 1. What we've now drawn is the molecular orbital diagram for ethylene. Right? And we could be asked at any different stage for what those different pieces are. Just because you took a picture, I figured we'd show the nicer one now. Right?
It was there, I just wanted the picture.
And we end up with those pictures showing all the interactions between them. Right? That's where they come from. You look and evaluate at each of those stages. Kind of make sense? Ish. As long as I get an ish, I'm okay. I'm actually seeing some nods of yes. So maybe I'll trust that as an ish. Okay? So big things that come out of molecular orbital theory. Okay? Sigma and pi. Single bonds result from sigma bonds. Okay? There's lots of s's strung through that. Okay? Single bonds have a free rotation. Okay? So it's not that it's necessarily irrelevant per se, it's that it's allowed. I'm allowed to rotate. Because if they directly overlap, when I rotate about that bond, the overlap doesn't change. Okay? This becomes super important when we move into nomenclature and when we move into chapter 4 and 5. We have to worry about sigma bond rotation. The pi bonds, all of our multi-bonds, okay, rotation is impossible because if we rotate, we destroy the overlap between those orbitals, which now takes us to a higher energy state. So we can't rotate pi bonds. Okay? Things that can kind of jump out and help us. Pi begins with p, which means the atomic orbitals used to make pi bonds are p orbitals. Pen. Sigma begins with s. So the types of orbitals used to make sigma bonds. This one's a little bit longer. We'll always, because we can put have in quotes, s. Okay? Really s character. Because an s orbital can be used to make a sigma bond, but so can an sp3. It has s character. Okay? So anytime you have s character associated with your molecular orbital, you're going to get a sigma bond. Okay? Hybridization. Okay? The more orbitals involved in your hybrid, the lower in electronegativity. That also means higher in energy. So anything that involves trends in electronegativity, we now have to remember that hybridization can affect that. That's a really big deal when it gets into chemical reactivity. Okay? It unfortunately is kind of a nuance of it, but that's a requirement of this section. Okay? We will come back to molecular orbital theory every so often. Okay? It becomes really important because molecular orbital theory tells us where electrons are. So if I break a bond, I'm now telling the electrons to go different directions. Well, that's going to change the molecular orbital diagram. If I'm making a bond, that's going to be the same deal. Okay? When we move forward, what we're trying to think about is where does the molecular orbital place the electron density? If the electron density is located between the atoms, that makes it lower in energy. If it places the electrons outside of the atoms, that increases the energy. So it's a question of evaluating the balance of how the electrons can move through the structure. And yes, that absolutely changes the reactivity. Right? I personally think this is a neat example, but it's kind of one of those extra things. So if you're interested, you can talk to me after class. I'll go through and look at it with you. My favorite section, this is how much I like nomenclature. I put everything that I think I need to know about nomenclature, and I put it on one slide. This one slide, you need to have memorized. Okay? This is nomenclature, if you will, in a nutshell. Okay? It does not cover everything, but it covers the bulk of your rules for nomenclature to an extent that in probably 70 to 80% of the questions you encounter, you'll be able to deal with. Okay? If you are specifically asked a nomenclature question, this probably won't work because this is the baseline easy stuff. Specific nomenclature questions ask tiers beyond that. Okay? For those of you that are curious about it, there's a book called the Gold Book. It's about twice the size of our textbook. That has all of the nomenclature rules in it. This is why I don't like nomenclature. Okay? And that said, that book gets updated every year, okay, with more rules because some jerk started inventing more compounds. Okay? I guarantee there's somebody out there being like, well, there isn't a rule to name this, so I'm going to make it so somebody has to name it. Okay? So if it feels daunting, that's because it kind of is. It just takes some practice. The big ones, 1 through 6, you have to know what those prefixes mean. Okay? What we're referencing is the number of carbons in our chain, meth, eth, prop, bute, pent, hex. After that, hept, oct, non, dec, undec, dodec. I think it's tridec and tetradec, but then I kind of lost my counting. Okay? It's close enough. Okay? The odds that you go beyond 10 is just highly unlikely. After that, you need to know your functional groups and what their base names are. So that's in red. Okay? We're going to spend most of the semester with the lowest priority functional groups, okay? 7 through 10. Halogens are so low in priority, we never really change the ending name. Okay? What is that, the suffix? Suffix. Okay? We never change the suffix. I think I'm right. Okay? For halides. We only add a prefix. Only in massive air quotes. Okay? Ethers. Equally low in priority as our halides. We'll end up naming each of the pieces of our ether based on the number of carbons, and then just tack oxy in there. Okay? After that, we start to see our suffixes come in. Okay? Alkanes, we change the ending to ane. So 10 carbons in a straight line becomes dec-ane. Throw a double bond in the middle of that chain. Okay? We would now have the alkene functional group, and it would become dec-ene. Okay? If I now throw an additional functional group in there on top of the alkene, okay, I need more information. Well, the higher priority functional groups take the first name. So notice for the alkene, it says end in ene, and then it says dash go to en. Why? Because what's happening with those arrows is we've added to our structure another functional group of higher priority. So we lose the suffix of the suffix, and it gets manipulated into one of the other ones. Okay? So there's kind of logical rules behind them. Okay? When in doubt, use the alphabet. Seems to work pretty well. Okay? As long as you know your alphabet. Your functional groups are listed by priority. So the highest priority dominates the name, and then we go through and deal with the rest of the pieces. Okay? That's the rule after the arrow. Rings, this is a huge one. Okay? If it doesn't say cyclo, don't draw it in a ring, because cyclo means cyclic. There's our ring. Okay? I can't describe enough how often everybody will make mistakes on that, including me. I'll go through and answer a question and be like, but this numbering doesn't make any sense, because if you draw it in a ring, it doesn't make any sense. If you draw it as a straight chain, it makes perfect sense. Okay? So remember your cyclo. When should you include the cyclo as your main chain? There's rules behind it, just like there's rules for everything. A lot of it comes down to priorities. If the rest of your structure is bigger than the ring, name the rest of the structure and put the ring on as a substituent. How do you know it's a substituent? Dang, I thought that was on there. Fudgesicle is really not there. How do we know it's a substituent? We change the suffix. The suffix is what ends your name. Okay? So how do I change the suffix to make sure it's not the end? Becomes YL. So if I have a single carbon that's a substituent, I can't call it methane because then it's just the single carbon. I want to call it a substituent, a piece of something else. There's a carbon coming out of the top of my head. I want to name that carbon. Okay? It becomes methylmine, because I was the original piece. Okay? So find your longest carbon chain that contains your highest priority. Okay? There are multiple ways to count: left to right, right to left, up to down to left to down to right to left, up, right. Yes. It's not a continuous straight line. It's wherever the longest carbon chain is, because those would all be connected by sigma bonds. And what can sigma bonds do? Freely rotate. So we can fold a structure up on top of itself and make you think it's shorter than it actually is. Okay? Make sure you always identify that longest carbon chain. Identify your highest priority functional group. Add that in as a name. Identify your substituents. Circle those. Define the location for each substituent. Every single one. I have 2 methyls coming out of my forehead. Okay? I have to go through and name each one. Okay? Well, the first one's coming out of Mike's head. So head methyl. The second one is also coming out of my head. So I can call head methyl, head methyl. It's kind of redundant. So instead we'll switch it to dimethyl. So I can just say head dimethyl. That only specified the location of one of those methyls. It would have to become head dimethyl. You have to list each of those substituents, or each of those positions. You want to use your smallest number. This goes back to dealing with your numbering your chain. Okay? And if in ties, use your smallest number overall. Use the alphabet. Hope you don't encounter a tie. Okay? The final step is you put all of those pieces together and you put it all in alphabetical order. And then you use your symbols, your numbers, and everything else. Numbers are separated from alphanumeric letters. Or sorry, alphabet. Numbers separate from letters with a dash. Numbers separated from other numbers with a comma. Okay? Different letters should theoretically all be jammed together into one big long string. Easy, right? So here you go. I will give you a minute. How do you identify the longest carbon chain? You just count them, right? Yes. Come up with a more strict procedure behind it. Okay? When you go through and identify, circle, because it's now identified as your main chain. So when you go through to name your compound, you've identified that extra piece. Okay, so this first one, yes, was a bit silly, but you would just circle it. You'd have 1, 2, 3, 4. Woohoo! Next one. 1, 2, 3, 4. Next one. Oh, that's a different shape. That must be different. 1, 2, 3, 4. What is the difference between the second and the third structure? A rotation about a single bond. Does that make those two compounds different? No, which means when we go through to name them, what should the names be? The same. All of the rules we go through and follow should match. That if you have two structures that you think are the same, they better come up with the same name. So nomenclature can help you in that respect if you're trying to identify relationships, because if you can name the compound and say, well, they're the same name, well, then they probably weren't different. And you should probably say they were identical. Okay? Yes, there's always exceptions. Okay? Let's go lower right, because I think that's easier. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
Now you just recount it.
I just recounted, so that doesn't work. Okay? People were drawing that out like, dang it, why'd you make me draw that? Don't trust me. God. Okay? Well, then 1, 2, 3, 4, 5, 6, 7, 8. Is that the longest carbon chain? No, because what happens to carbon 8? It's connected to carbon 4. The chain is looping back on itself. That means you've named a piece and a ring. Those are two separate things. You can't loop them together. Okay, so that numbering was wrong. Okay, so the next part, 1, 2, 3. I won't include that as a 4, because where's 4? 4 is part of the ring, so I'll start that as 1, 2, 3, 4, 5. For the red one, notice I didn't include that piece. Okay, it would be a substituent on that. Okay? Where's my main chain? Which is the longest carbon chain? The cyclostructure. So this gets named or numbered as 1, 2, 3, 4, 5. Purple, the red, was invalid. Okay? So the cyclostructure is my main chain. The rest is a substituent on said main chain, because the cyclostructure has more carbons than the other part. The last one, well, if I go through, 1, 2, 3, 4, 5, 6, 7, right? That's not the longest. Where's the longest? Okay. It does not have to be a straight line. Okay. Let's deal with, whoops, go through and name this one, because I think this one's the most interesting of the ones listed here. Okay. I've now circled my substituents. How would I put this together? Well, the number of carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I would be a non-ane or non. How are all the carbons connected? Sigma bonds. Okay. That is only found in my alkanes, so this becomes non-ane. What are these substituents? Well, I have a single carbon, so that's a meth. Ol is a substituent. I have 2 carbons, so that's an eth substituent. I'm running out of colors. Blue? That's fine, let's just do blue. Eth ol. Where are those substituents located? Well, now I'd have to go through a number. I could number from left to right or right to left. The answer is going to be right to left. Because when we number right to left at position 3, oh, this is a fun one. 4, 5, 6, 7, 8. That's an 8. 9. Versus we numbered the other way. 2, 3, 4, 5, 6, 7, 8, 9. Purple ends up getting better. We do get 2, actually no, that one's at position 4 versus position 3. Right? So 1, 2, 3 in purple makes more sense. So my methyl is at position 3, so 3-methyl, 4-ethyl, 6-ethyl. Yeah?
Can you explain one more time why you said it makes more sense?
If we go right to left, our first substituent shows up at what position? Sorry, right to left. Right to left, it shows up at position 3. Left to right, where does it show up? Position 4. Look at our numbering. Yeah, there are lots of numbers going across these. Yep. If we had to string our name together, okay, it goes alphabetical in order. Which comes first, ethyl or methyl? Ethyl. How many ethyls are there? 2, so it's diethyl. Where are they located? Position 4 and position 6. 4,6 diethyl. 3 methyl nonane. Mother monkey, yes. And this is simple.
So when you're listing the alphabetical one first, for that like prefix di, do you take that into account?
No, the prefix doesn't count.
Okay.
Yeah.
But before the diethyl, is that like 4.6 or like
4 comma 6. 4 comma 6 dash diethyl dash 3 dash methyl nonane. Yes. For my numbering? So if we go through and look at the numbering, I've got 2 numbering patterns in there, purple and black. Screw it. I'm just going to, oops, that was not an eraser. That's also not an eraser. Let's number it the way you were suggesting in black, left to right. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah? The first substituent shows up at what position? At position 1, there's nothing. There's nothing special attached, only the main chain. This is why it's helpful to circle the main chain. Is there anything coming out of position 1? No. The only thing coming out would be 2, but that's in the main chain, so there's no substituent there. So where do I have something actually coming out of my main chain? Position 4 is my first position. If we numbered it the other direction, now in purple, 1, 2, 3, 4, 5, 6, 7, 8, 9, where's the first thing poking out? Position 3. Which is lower, 3 or 4? 3, number in purple. Okay. The other way to think about it is organic chemists are stupid. We don't like math, so we pick the smallest numbers humanly possible when we go through to solve things.
Is the 3-ethyl supposed to go first? Lower.
There is no 3-ethyl.
Or sorry, 3-methyl. Like when you named it 3-methyl, then 4,6 diethyl.
So the 3 is your methyl, but when you put all of your pieces into your name gets organized alphabetically. Ethyl comes before methyl because I'm pretty sure E comes before methyl. Right? I do get that wrong every so often, so it's good to call me out. Okay.
Question on the cyclo.
Yeah.
1, 2 as the top. Is that the order that it should always be?
So if we were dealing with naming that bottom one the cyclo, because that's an extra fun one.
And then what if you had another?
Cyclopentane. Okay, what is the name of our substituent now? Okay. Well, now how do we number that? Where's the first position in that structure? It's where it connects to the main chain. That, by definition, is position 1. Where's my longest carbon? 2, 3. Why has that become problematic? There's a substituent on my substituent. Yes.
Yes.
Yes, there is.
Okay.
So how do we go through and name that one? Because that's a beast. I needed to run a little bit of space here. Sorry. So there is a methyl located at position 2 on my prop But I can't call it propane because the propane is a substituent. So that is propol. I could then delete that big space in between, and I can say 2-methyl-propyl cyclopentane. Why would that then be confusing? It looks like the 2-methyl is referencing being connected to the cyclopentane, right? But that's not true because I didn't specify a location for the propyl. This 2 is actually a substituent on the propyl, not a substituent on the cyclopentane. What? Yes. Okay. So how can we clarify to make sure that the 2 applies to the propyl and not to the cyclopentane? I can drop parentheses around that because that now in black is my substituent. Where was that substituent located? Position 1, and it becomes 1,2-methylpropyl cyclopentane.
That's the impact name, right?
Yes. You could go through and use the common name for this substituent. Okay? The reason why I kind of left that off is you're not officially responsible for common names. So you get some kind of borderline stuff happening with common names. Right? So each of these names is wrong. I want to know why and how you would fix it. So this section of the class, which one do you want to do? 1, 2, 3. If you don't choose soon, I'm going to choose for you, and I'm going to pick the hardest one. I heard 3. Okay. I have no idea which one's the hardest one. But you guys are doing 3. This side of the class, which one do you want to do? 1 or 2? I heard 2. So you guys are doing 2. I'm going to do 1. Okay, so go through, do the best that you can with it. And for those of you at home, yes, I'm going to record this as I go through and do it, but I'm not going to talk over it. Okay, now that I got mine solved, I'll let you. Okay, so I believe I've got them all up there. So in the first one, the issue is it only specifies one of those methyls, the location. It needs to say 3,3 because it's a dimethyl. Okay. The second one, 3-dimethyl cyclohexane. Okay. It's a cyclohexane. Okay. There's 2 methyls at position 3, so there's an issue with the 3,3, but then there's also a weird, why does it say 3,3? If both the methyls are at the exact same location, they need to be the lowest number. The lowest number would be 1. So the 3 makes doubly no sense. They're located at 1, 1. It is optional to specify that 1, 1. Okay, why is it optional? By definition, that's where they go. So because of that, you don't have to include the 1, 1. Sometimes you'll see it dropped, sometimes you'll see it kept on. Right. The last one, I'm a little bit nervous because I only found one mistake and it's still the numbering issue. So I'm concerned that maybe I was trying to do something else, but it works. This one's a little bit different because we have a 2 in the middle of the name. That 2 is as close as possible to what? the functional group that it's referencing. At position 2, I have an all. The all suffix meant an alcohol. I need to draw an OH. Okay? So if I were to fix that name, it again needs to be 3,3-dimethyl hexane 2-ol. Okay? Kind of makes sense? So here's the massive thing out of this. Was I able to draw the structure in all 3 cases? Yes. So everybody knew what the structure was based off of that name, and yet the 3 names that were provided are all considered wrong. Why? Because you didn't follow the rules of nomenclature. This is why I just said, screw it, I don't want to deal with it. Okay? You need to be able to read a name and come to the structure. That is important. The reverse aspect of going from the structure to the name becomes much less so important, but it is still important for the sake of the class. I have to kind of say that even though I don't like it. Okay? And really it comes down to, did you know the rule that makes you do the way you do?
Question on 1 and
Yes.
3, you have the A, N, E.
Yes.
All single sigmas, but isn't 3 also an all single?
It is all single bonds, which is why when you look at the green main chain, they're all single bonds. Okay? I do still have to specify, and I think the way I've been referencing up here is the hybridization of each of the carbons. Okay? So unless I have to specify that ane, if I don't say ane, what's the hybridization for each carbon? Well, I wouldn't know.
Why'd you put an E on the 1 and not on 3?
Up here, that E is the suffix of suffixes to cap that name. What did I change it to? I changed it to all here because there was a higher priority functional group. And up here, I could end it with an E because there wasn't a higher priority functional group. I could end it at the alkane.
So you can
You should always end your name with the highest priority functional group. Yes. Bless you.
So then you wouldn't have to pronounce all the 3s and 2s, you just say dimethyl hexane, right?
For this last one, you have to say 3,3-dimethyl hexane 2-ol. You have to. If you leave the numbers out, you don't get that structure.
Okay.
Right. It's too ambiguous. You'd end up with a bunch of different structures.
Okay, so when is it at 1, 1?
When is the 1,1 optional? By definition, where's your ring start? Your lowest number. So your first substituent's going to go to the lowest number. Since it's a ring, the lowest number will be 1. The 1, 1 up in the ring structure is optional because it's a ring. In question 3, and for that matter question 1, neither one of them are rings. You have to specify the locations. Okay. If I added on another substituent, let's say I did this. Okay, so if we delete everything, everything's gone. See that new structure? How would I name that? Well, it is a cyclohexane. Now what do I have for substituents? Well, so first there's my main chain. Substituent, substituent, substituent. Those are each methyls. So for those of you at home, this is exactly what I would do. I would name each substituent. Because they're all methyls, I could then go through and say methyl here, because it'll be my first one. It's now trimethyl, where each of those methyls located. 1, 1, 3. Now I have to include the number because I need to specify where that third methyl is. I'm forced to include that 3. The instant I drop the 3 in, I have to specify the other ones. Okay?
It wouldn't matter if they put it on the one on the very bottom because it's the exact same structure, right?
And the one on the very bottom, it's not going to matter because it's not a ring.
I'm just saying, if your number 1 is there instead of, oh, sorry.
Were you looking at this one?
If your 2, and you went 1, 2, 3, or you went 1, 2, 3.
Like you put the methyl down on the bottom.
You took that single methyl, yeah. Put it, no, the hexane one.
On
Or
the
a cycle,
cycle.
sorry. We're talking about cycling, you put the 3,
Oh, you did that?
I did that instead, would that be?
Yeah, that's exactly the same thing. Yep. Right. All that would be a flip. So maybe people at home, I don't know, we're saying that structure versus this structure are identical. Yep. You would end up just changing your numerical order because you want the lowest number. Okay. Nomenclature, as much as I badmouth it, really isn't that bad. It is just the sequence of rules. You just have to practice those rules. Okay. So practice it if you decide it's worthy enough for your effort. Okay. Where we would then move into is officially Chapter 4. And if we look at the word butanes, C4H10, why do they have the S? Because with butane, I could have drawn it as 4 carbons as a straight line, or as that. Both of those have the exact same number of carbons and hydrogens. Right? So I have to get a little bit more specific when I go through a name. Why do we start immediately with butanes and not say with methane then? Well, how would I draw methane? Maybe just a point if I really wanted to abbreviate it. What other way could I draw it? Well, that's about it. Okay. Why not ethane? C2H6. How many different ways can I connect those carbons? Can't. Propane? Well, notice with propane, whoops, could have gone that, or I could have gone like that. Oh, see, I put it in a different spot. Oh, no, I didn't. All I did was just turn it. Right? So propane doesn't have that issue either. Butanes, however, do, and that's why we have to watch out for butanes, or that's why butanes start to come up as our kind of initial target. Okay? What is the relationship now between those structures? Okay. Well, they're both 4 carbons. They both have 10 hydrogens. Okay. Can I call them the same thing? No. Could I call them different?
Yes.
Well, they sure look different. How about I throw that next one in? We just said these two were different. What's the relationship between these two? That has an extra carbon. So are those the same? No, absolutely not. Too many carbons can't be the same. So they're different? Yes. Okay. Is the red different, the same, or different? Or that's not red. Orange. Is the orange different, the same, or different from the purple different? It's a different. Right? Which means the word different would have 2 different meanings depending on the context that I'm looking at. That is confusing. So we can't call them the same thing. This is where we start introducing different, for lack of a better word, ways to reference our compounds. Different means that the molecular formulas are different. That would have been our purple different. Those are different from each other. The next one, identical. The formulas are the same and the structures superimpose, which is a hard little word. We'll look at that in a second. And the last one, isomers. The molecular formulas are the same and the structures are not superimposable. Okay, so we'll try a couple examples here. Okay, this is fun for the people at home. You won't get to see anything. These pens, okay, ignore the color for the moment. Okay, are they superimposable? Okay. What we're saying is, would they completely overlap with each other? So there's superimposable and there's superposable. Okay. For the grammarians out there, nothing is, I believe it's this way, nothing is superimposable. Okay? It can't be superimposable because they're physical objects. Superimposable means they exactly overlap on top of each other. There's an object there, it can't physically exist in the same space. So nothing is superimposable, I believe. So depending on the level of grammatically correctness you want to get into, you may hear superposable. Okay? Superposable is saying if I ghosted one and overlaid them, would they occupy the same space? Okay? Yes. They're both looking at the same concept. These both occupy the same space. How about this pen now? The cap's different. They're not superimposable or posable. Look, they're even different heights. Right? So these two are not superimposable. Right? Let's move to your hands. This is an example people can use at home. Are my hands superimposable? Everybody just goes through and does this. It says, yep, they absolutely perfectly overlap. Superimposable means everything about your hand must overlap everything about the other hand. You're like, but it does. No, they have to occupy the same space. That means the top of my hand must occupy the same space as the top of my other hand, which means I'm not slapping them together. I'm sliding them over the top of each other. Are they superimposable? No. Okay? What is the action of me slapping my hands together? And don't say clapping. They're mirror images. Okay? So we get this issue of superposability. Do they exactly occupy the same space? And then this issue of mirror images. Right? They seem very similar, but entirely different. They can't lead you to more different pathways. Okay? So, we need to be aware of the different relationships and be able to identify those relationships. Okay? This becomes important when we look at our alkanes. It's not a big deal with our methane, because when we look at our methane, there really isn't anything special about our methane. Okay? We can spin, flip, or rotate any of those bonds, and it looks exactly the same. Nothing changes. Okay? If we change our viewpoint on the molecule, would our drawing change? Okay? If we tried to draw this as is right now, how would you go through and draw it? Really badly. Yeah. Most people, yes. Right? Well, there was this kind of whitey ball, but I've got a black line, so that doesn't really work. With them on down, and then I had this big black ball. I can color that one. Okay? And then somewhere to the right, it had another line, and it had this. And then this other one was coming at me, so let's kind of do, but its line was somewhere in the middle there, like that. And then there was another one that was kind of that was in the back, so I'll draw it a little bit smaller because it was further away. And we'll show that connection in. Oh, but I drew it in such a way where, oh, see, already messed up. See, there we go. There we go. Now I've drawn my model. And I even showed all this three-dimensional aspect to it. How many of you have taken an art class? Okay. Those of you that have taken an art class, guess what? Bust out your crayons. Or other things. You probably use things other than crayons. Okay. That's what Chapter 4 and Chapter 5 is all about. How do we draw a three-dimensional object in 2 dimensions without losing information? I could go through and draw it like that, but that took time. The way that we draw instead would be this. I can get the same meaning with less effort. The hydrogens are in the plane of the paper. So by being in the plane of the paper, I will use a solid line to represent them. The hydrogen in front here is wedged. It's coming out at me, and by coming out at me, it gets bigger. That's why I'm showing that wedge getting bigger towards you. The dash. Have you ever seen something in the distance, in the Arizona heat, that kind of shimmery look? Okay, it's kind of a mirage, and you see those kind of waviness. That hydrogen is so far away, it's miraging on me. That's what's happening. That's what I'm trying to represent. Okay? Would I be able to see this? all the same pieces, right? Is it possible for me to orient the molecule so that I can see that? So, plane of the paper, there's the wedge coming at you. I need to get that dash, instead of being that way, up here. Everybody see that? So I need to just pull that guy up here. What happened?
So the H is coming towards.
Everything else changed. This structure, impossible. Drawing it won't necessarily lose you points, but what will likely happen is you will misinterpret your drawing and get the wrong answer. So when you're drawing your structures, it is imperative to know what the model is supposed to look like. That is the point of our drawings. Not because we're trying to make it look pretty, but so that we're trying to understand what the three-dimensional object is doing. We'll pick up there whatever the next day is.